Hello, everybody. Gonna start in just a second here. Cool. I think I'm gonna start. All right. Welcome to the second semester. I gotta say, really. Okay, I'm back. Sorry about that. So, yeah, this is the second semester. I wanted to say really nice job to this class in particular on the final. I thought it was going to not go well, and it ended up going pretty well across the board for you guys. So I'm pretty impressed. Um, so let me talk a little bit about the second semester. In the second semester, we basically got 4 more topics left. Okay, so sort of by the maybe towards the end of the second triad, we'll have completed the official content for the AP Physics 1 course, and then we'll review for the AP exam. And then after that, after you guys take the AP exam, if you're going to do that, we will have some projects, try and do some labs, and just kind of do fun stuff and be more relaxed for the remainder of the school year. So usually people get a higher grade the second semester than the first because of this, because there's a project that will sort of pad your grade. And we'll have a midterm at the first triad, and then we'll have the final at the end of the second triad. So your final will be at the end of the second triad, and then we will have a project as a major grade for the third triad. Okay, so let me know in the Zoom room if you have any questions about that. All right, so I'm going to go ahead and get started. So for the next few weeks, we're going to be talking about something called simple harmonic motion, which is also known as SHM. And so if you have simple harmonic motion, what that means is that your position as a function of time is given by a cosine of omega t plus phi. All right. So now Okay, so what do these constants mean? Well, first of all, let's just draw the position as a function of time. And I'm actually going to add a constant here too. Okay. So your position as a function of time looks like this. So it's a sine or a cosine. Okay. Now, if we look at the size of the vibration from the center line, that is the amplitude A. So this is called the amplitude. All right. So however tall it is. So to have a bigger amplitude means that the swings are larger. Okay. The period is the time it takes to complete one vibration. Okay. So you have an object that is going back and forth. Its position as a function of time is going back and forth and back and forth. The time it takes to go back and forth once, okay, is one period. T. So if you take the time at which one peak happens and then the time at which the second peak happens, and you take the difference between those two times, that is the period. And it turns out that the period is related to this number omega. Okay, so this omega is related to the period. According to period is 2 pi over omega. Okay, so that's an important equation. It relates this number omega to the period. T is, of course, the time. Now, what is phi? Well, to understand what phi does is you have to remember your graph of like f of x versus f of x minus 5. Can you tell me, type it into the chat if you know what it means to graph f of x versus the quantity f of x minus 5. Type it into the chat if you know what that what the difference between those graphs would be. Exactly. So you're shifting the graph horizontally. Okay. So this is a horizontally shifted, not down 5. It's horizontally. So this is a horizontal shift. Okay. So basically, what this variable does, phi. This is the Greek letter phi. Phi shifts the graph horizontally. So it's still simple harmonic motion if you have, if it starts here, or maybe it starts at the origin, like that. So this would be more of like a cosine. This would be more of a sine. You could have something that goes like this. That's going to be a negative sign. So all of these are the same graph. They're just shifted horizontally. Maybe you've noticed that if you take a cosine graph and you shift it horizontally, it can be a sine graph, or it can be a negative sine graph, or if you shift it, it can be a negative cosine graph. So All this is a horizontal shift, okay? Now, this C is called the equilibrium position. Okay? And so maybe you have graphed f of x versus the graph of f of x plus 5. So these are different ideas here, because this is the minus 5 is in the parentheses, so it's in the argument of the function f. Here it's the plus is outside. And so if you remember graphing functions, you know that adding something to the end basically shifts the graph vertically. Okay? By a certain amount. Okay? So basically C is what the graph is vibrating about. So if you had a graph that looks like this, okay, here's position, here's time, and maybe the graph looks like this. So you can see how the vibration is about this central point. This is what the constant C is, all right? So the constant C is the equilibrium position. It's the central value if something is undergoing simple harmonic motion. So in this case, because it is vibrating about x equals 0, that's the central location of this vibration. This graph has C equals 0. This graph does not have C equals 0. So if you have an equilibrium position that is not 0, then the amplitude is still the distance from the center line. Okay, so that would be the amplitude. This, I guess that's a little bit too small to see. This is the amplitude. Okay. So let's do a couple of examples here. All right. So my first example is, suppose we have some simple harmonic motion. And what if we have x of t equals -4 sine of, let's say, 35t plus 7. Okay. So what is this going to look like? Well, first of all, what is the amplitude? The amplitude, A, is the size of the vibration. So big amplitude versus small amplitude, like this would be small amplitude. This would be big amplitude. So it's how big is that vibration. Okay. And to determine the amplitude, you look at, see how we want to look at our model here for simple harmonic motion. Okay. So the amplitude is the number that multiplies the trig function. So the amplitude, the number multiplying the trig function is 4. Right? I should say it's the absolute value of that number. So the amplitude in this case is 4 meters. That's the size of the back and forth. Okay. Now, so that just comes from comparison. The number in front of the trig function is the amplitude. Okay. The fact that it's negative, all that means is it's just going to vibrate down before it vibrates up. So that doesn't really have any impact on the amplitude. Then we can see that whatever the number is that is multiplying the time, that is related to, that's called omega, and it is related to the period according to 2 pi over omega. All right. So if we look at this, we can see that 35 is multiplying the time. So the period t is 2 pi over omega, which is going to be 2 pi over 35. And so the period of that is going to be 0.18 seconds. Okay. So the period, 0.18 seconds. The amplitude is 4 meters. Now, if we look at the thing that's added on to the very end, that is the equilibrium position. Okay. So we can see in our model of simple harmonic motion, the thing that is added on at the very end, that's the equilibrium position. So we can see that 7 right here is the equilibrium position. So equilibrium position, C is equal to 7 meters. Okay, so what if we were going to graph this? So we're going to graph the position as a function of time. Okay, so we have the position in meters, and we have the time in seconds. Okay, and we can see that the equilibrium position is at 7. Okay, so here is x equals 7. It's going to be vibrating about that spot. Okay, and if we see the amplitude is 4, so that means to say that the amplitude is 4 means that it can swing 4 above its equilibrium position, or it can go 4 below the equilibrium position. Okay, so 4 above 7 would be going up to 11, and 4 below is going to be going down to 3. Okay, so this is a wiggle that goes between 7 and 3. All right. So these are kind of the bounds of this simple harmonic motion right here. These are the bounds. Okay. So now we can see that this is a negative sign. Okay. This graph right here is sine. Negative sign is the flip of that. So the graph is going to look like negative sign, which is this one right here. So if I were to just sketch out a negative sign, looks like this. Okay, and I can see that the graph restarts. So we can see that it starts out at 7 going down, and we can see that the next time it, now here this is not one period because here it's going up as it crosses 7. So it has a positive velocity while it crosses 7. But we can see here it's going down and it crosses 7. So one period would be this amount of time right here. Okay, because that's when we have a dip, we have a valley, and we have a mountain. We come back to the same spot. So this would be 0.18 seconds later. Okay. So that is how we go from an equation. So you should know that the point of this example is that you should know how to go from an equation to getting the amplitude, the period, and the equilibrium position, and then taking those and going to a graph. Okay? So, and by the way, this would be right here. This is a second period. So this would be at 0.35 0.36 seconds. All right. Also, we should be able to go from a graph to producing the equation of the position of the particle as a function of time. Okay, so let's do an example that shows how that would work. All right, so what if I have a position as a function of time? So here's position in meters and time in seconds. All right, and let's say we have, this is -5. And let's say this is +1. And this is -11. Okay, so, and let's say this is 0.2 seconds. This is 0.6. This is 0.8. Okay. All right. So we have this graph. Sorry, that took me a while to draw. Okay. So this part should be pretty easy. Who can type into the chat, what is the equilibrium position C of this simple harmonic motion? So what is the point, the x coordinate, the position that this particle is vibrating about? So it's going back and forth about a certain location. Type it in the chat if you know. -5, excellent. Okay, so that means that C is -5 meters. Okay, now how far away from -5 meters does this particle stray? So we know that it's vibrating or oscillating about x equals -5 meters. How far away does it go? And that can tell us the amplitude. So who can determine the amplitude? The amplitude is 6 meters. Very good. So how do we know it's 6? Is because the farthest that this graph goes from x equals -5 is 6 meters away. So the distance between -5 and -11 is 6. The distance between -5 and +1 is 6. So the amplitude is 6 meters. Okay. Now we can figure out the period. So the period, all right, the period, we can see that it starts out on a peak. So when does it go back to a peak? We can see that it gets back to a peak in 0.8 seconds. So the period is 0.8 seconds. Okay. And so we can use that to determine the omega. So period is 2 pi over omega. So that means that 0.8 is 2 pi over omega, which tells me that omega is, let me work that out, 2 times pi divided by period. That says omega is 7.85 radians per second. Okay, 7.85 radians per second. So the reason that it has the variable omega is because it has the same units as angular velocity, which was also radians per second. So that's why it's called omega. All right, now who can tell me which trig function does this look like? And I'll give you three options. It could be sine, it could be negative sine, it could be cosine, or it could be negative cosine. Which trig function do you think we have here? Because all of the trig functions represent simple harmonic motion. What makes it simple harmonic motion is your position as a function of time looks like a sine graph or a cosine graph or some combination of the two. All right? So what does this look like? So don't even worry about where the axes are. Like, just look at the shape of that. Very good. Yeah, excellent. So you can see that it starts out on a peak. It starts out at its maximum, and then it goes down from there. So that is cosine that does that. So if I were to look at my position as a function of time, it's going to be A, which is 6, cosine of omega, which is 7.8, t, minus 5. So that is going to be my position as a function of time. All right. So notice how all this Greek letter phi does is allows me to write a general form with only one trig function. But really what it does is this: if you take a cosine graph and you shift it horizontally, it turns it from sine to cosine to negative cosine, one of those four. Okay. So I'm just writing it with a cosine function. All right. So that's kind of the first part, is just introducing you to what simple harmonic motion is. So simple harmonic motion means that the position as a function of time is a trig function. All right. So now we want to ask ourselves the question, what equation of motion will result in SHM? Okay. And so I'm going to tell you the equation, and then I'll show you why. All right. The equation is minus omega squared x equals A. So omega squared, okay, omega squared, this is the same omega that appeared in the other equation. So this is the same omega where period is 2 pi over omega, okay? And so basically omega squared is going to be a property of the system. And I'll explain in the next lesson how we can figure out what omega is. X is the position, and A is the acceleration. Okay. And so just to remind you, in a position time graph, acceleration is the bendiness of the graph. Okay. So let's try to understand, why does this equation result in simple harmonic motion? Okay. So if we have, let's suppose we have a position as a function of time. Okay. And let's suppose that the position is positive. So if the position is, because here's position 0, up above is positive, down below is negative positions. So if your position is positive, that means we have a positive number times omega squared. Any number squared is going to be positive. So we have a positive number times a positive number times a negative. A positive times a positive times a negative, that's going to be a negative number when you multiply that out. It's like, 3 times 5 times negative 7. That's going to be a negative number, right, when you multiply all that together. So that means that when the position is positive, the acceleration is negative. Okay? So when x is greater than 0, the acceleration is less than 0. So that means, because acceleration is bendiness, this graph is going to be bendy down. So it's going to bend down like this. Okay? And we can see that if it keeps bending down, it's going to eventually cross. All right? So now we have a negative position. If we have a negative position, we have a negative number times omega squared, which is a negative number. Or sorry, omega squared is a positive number, times negative. Okay, so we have a negative times a positive times a negative, which is a negative number. Okay, so when x is less than 0, the acceleration is positive. And if you have a positive acceleration, that means you are bendy up. So the graph, so once it crosses below, now it's going to be bendy up all of a sudden. It's going to go, and it's going to cross, and now the position is positive, so it's going to be bendy down, and then it's going to be bendy up, and it's going to be bendy down and bendy up, and it's just going to repeat. So it's just going to go, so we get something that looks like a sine or a cosine. Okay. One of the things I want to point out here is, in the context of simple harmonic motion, capital A is amplitude and lowercase a is acceleration. So those are two different things. All right. So just be aware of that. I just thought of that. All right. So so that's the reason why this is true. Okay. Now, what if you have an equilibrium position that is not 0? This is with an equilibrium position of 0. The general form of the equation, if the equilibrium position is not 0, is negative omega squared times the quantity x minus c equals the acceleration. Okay. So why does this make, so this is the general equation. So let me go ahead and do one more example, and then we'll go to the Zoom room. Okay, so what if the equation of motion is, let's suppose that the equation of motion is negative 300 x plus 75 equals 0.2a. All right. So the first thing I'm going to do is, we can see, so what we're trying to do is we're trying to figure out what is the period. okay? And then we also want to figure out what is the equilibrium position, okay? So what we want to do is we want to try and put the equation in this form, okay? And we can see that it's a times, or it's just a, on the right-hand side, we just have acceleration by itself. Here, we have 0.2a. So what I'm going to do is I'm going to divide both sides by 0.2, all right? So dividing both sides by 0.2, I get negative 1500x plus 375 equals a. All right. Now, what would happen if I were to multiply out the left-hand side of this equation? All right. If I were to multiply out the left-hand side, I multiply negative omega squared, I get negative omega squared x plus omega squared c. So negative times a negative equals a positive, so that's why this is a positive here, equals acceleration. So let's compare it. I have negative omega squared x plus omega squared c equals acceleration. So what I can see from that, okay, first of all, just by comparison, I can see that omega squared is 1500. All right? And then furthermore, I can see omega squared c, by comparison, is 375. All right? But remember, omega squared is 1500. So I have 1500c equals 375. And I can get that c is 375 over 1500. Which is 0.25 meters. So this is the equilibrium position, 0.25 meters. Okay? Now, how do we get the period? Well, omega squared is 1500, so that means that omega, I got to take the square root of that, is 38.7 radians per second. And then the period is 2 pi over omega, so that would be 2 pi over 38.75. 0.16 seconds. Okay? So I determined the period and the equilibrium position from that. All right? You cannot determine the amplitude from the equation of motion. The reason is that basically the system is what determines the period and the equilibrium position, but the experimenter determines the amplitude. And I'll explain that more on in Friday's lesson, where we talk about some specific examples of simple harmonic motion systems. So what we've done today is we've explained what is simple harmonic motion, okay? So what is simple harmonic motion? It means your position as a function of time is sine or cosine. And then we've described some of the characteristics of simple harmonic motion. So all simple harmonic motion has an amplitude, has a period, and it has an equilibrium position, which is the point that it is vibrating about, okay? And then we learned how to identify those quantities if you're given an equation or if you're given a graph, okay? And then we learned the equation of motion that will result in simple harmonic motion. Next time, we will give some examples of specific simple harmonic motion systems, okay? So that is my lesson for today, and